Thank you. So Lucia, after this conference was announced, she came in and she said, "Oh, it's very exciting. We have to go to Singapore and talk about, tell people all the interesting stuff that Charlie's done." And she said, "And I'll talk about covering rays." So, I mean, it's not that hard to also find something not covering rays that Charlie has done. But I wanted to tell you about something that is close to my heart. And that is orderings of the blocks of designs. I'm very interested in gray codes. And after a number of years of me thinking about gray codes, I thought, well, what's a gray code of a design? And I had a PhD student, Megan Dewar, who wrote her thesis on ordering the blocks of designs, different paradigms for ordering them and things like that. And her external examiner, who was not Charlie, it was David Pike. After the defense, he said, I can't think how you're going to turn this book into papers. He said, why don't you think about turning it into a monograph? And so we did. It was a very interesting thing to do, and it's been published in the CMS series of monographs. And it's all about different ways of ordering the blocks of designs. Charlie appears in the bibliography several times, and I want to tell you about those times and what they're about. I should say there are a number of different paradigms for ordering the blocks of design. There are ones where you want, say, consecutive blocks of the design to only differ in a few points. And this is something that Wal Wallace and a large group of other mathematicians did, and they're called single change covering designs. They're very nice stuff. And those are really, almost what you would think of as a gray code, or universal cycle is kind of like a generalization of a De Broglie cycle. But there are also configuration orderings, and that's where I'm going to concentrate this talk. But there are other paradigms of ordering, not just those two. And Charlie has contributed to those orderings, and I'll mention them along the way, but that's not going to be my focus. Okay, so, and one of the neat things about ordering the blocks of the design is that they have applications, notably to erasure correcting codes, tournament scheduling, which was a PhD thesis of another student of Eric Mendelssohn's, Peter Rodney. His thesis is really all about ordering the blocks of designs in particular ways that are useful in sports tournaments. There's reliability testing, which is covering arrays. There's papers on ordering the blocks, the tests of a covering array. There's group testing and there's statistical testing, and I'm sure there are others that we didn't find. In this talk, I'm going to concentrate on these two, where Charlie has has spurred the notion of ordering the blocks of designs, motivated by these applications. And the first one is erasure correcting codes. And disk array storage is a response, in part, to Moore's law. We have, and it seems to still be continuing, have every 18 months since the invention of the microprocessor, doubled our capacity speed-wise, and that's kept steady, but there have not been corresponding advances in the size of storage. And one way to cope with that is to keep your data on a large set of hard drives. So I'm going to write some piece of data. I take one chunk, write it to the first one, second chunk, write it to the second one, and so on. That's called data striping. And it has two benefits. One is, well, it gives you large storage capacity, right? Add up the terabytes of those drives, and you can store that much. And the second thing that's really great is, because I'm chopping up my data and writing it, each one of those drives can have its own bus, and I actually have access times that are really fast. So it scales in that sense. It doesn't get slower as it gets bigger. But there is an issue. So I don't know if any of you have read, there's a paper published by some Google scientists in 2007. Bill Martin turned me on to this paper. This is a fascinating paper. I really encourage everyone to go read it. I'm being honest, it's not facetious. They did a study of 100,000 hard drives that they have used. And one of the really neat things is that these were actually cheap hard drives, like the kind you and I buy, right, in our computers, not enterprise hard drives. And of the many, many, many things they discovered was that the annual failure rate of drives was at least 4%. Whereas if you calculate what the manufacturer states for the expected lifetime between errors, you have to go and do a calculation, it would be a little bit less than 2. So Google found that drives are, they are twice as likely to fail than the manufacturers are telling you. And they, at one point in the paper, they say, oh, and we know which, we've categorized failure rates by manufacturers, but unfortunately we're not allowed to tell you. Which does kind of give a lie to the fact that Google wants to make all information accessible and transparent. Oh well. Another interesting thing from this paper. So, do you think a hard drive would be more likely to fail if it was running here, say at the bottom end of this room where it's cooler, or outside? Who thinks it would be more likely to fail in here and outside? Okay, yeah, so you have to ignore humidity. But they have this little table in the thing. It's a table of, in their system, the mean running ambient temperature of the room these drives are on, okay? And it looks like this, right? So this is 20 degrees Celsius, and this is 50. Okay, so most of their drives are running at 30 or so, okay? And they also publish the failure rate by temperature, and it looks like this. I think this is the most interesting thing in this whole article about the optimal running temperature for a drive is 45 degrees Celsius. It's amazing. We keep all of our computers in cold rooms. For drives, at least, that's actually not optimal. It's causing more errors. Anyway, I digress. So, we've got a 4% failure rate. There are other kinds of failures. This is essentially a failure where the whole drive's gone, you can't access anything more. There are failures which mean parts of it are gone. And so, generally speaking, the failure rates will be higher than that if you want to access any one particular piece of data. So, I could find information on this particular storage array, although I think this is out of date already, but IBM has this 120 petabyte storage array, and it's got 200,000 hard drives. 22 of their hard drives per day are going to catastrophically fail, and all the data will be unrecoverable. 22 a day, at least. And that doesn't include other kinds of failures where you can't get parts of the data that are stored on there. So if you're going to store your data on arrays, you have a failure problem, right? Great, large capacity, great, it's fast because of parallelism, but you have very high data failure rate, inability to access the data. So as a response to that, we have developed what are called erasure resilient or erasure correcting codes. Suppose I have a drive that goes bad, I have to pull it out, I put a new drive in, and there has to be a system by which it can go and reconstruct the data that was on that drive. So we have to have some redundancy built in if you were going to do disk arrays. Okay, so here's an example of an erasure correcting code. This is 10 information disks and 5 parity check disks. And it can handle 2 erasures. Okay, and I'm going to tell you how it works. So it comes from K5. So this is the parity check matrix. Here are the parity check disks. And the columns of the information disks are just all of the pairs of the 5 elements. So when I write to this hard drive some piece of information, I have to go and update this parity check disk and that parity check disk. And if I write to this one, I have to update these 2. So on. It's very straightforward and simple. And there's a couple interesting measures. An update penalty is, well, I write a disk. How many disks over here check disks do I have to update? This has an update penalty of 2. And update penalty is very closely related to what you can correct, because if you can correct, say, K catastrophic failures, then, and you can't do K plus 1, then that 1, imagine a K plus 1 set, when you change the information on that 1, those other K must be ones that you have to update. And so it's easy, or it's reasonably easy to see that the best update penalty you could get, you want it low, would be the same as your K. So in this case, it's 2. Now, the next most important thing after update penalty is consecutive writes. Most of the time that we are taking data and writing it to disk, we are accessing more or less a contiguous chunk. And so suppose I wanted to write to these 3 disks. I can go and check which parity checks disks do I have to access. I have to access these 2, and these 2, and these 2. I already accessed that one, but all 5. So that's not that great. And I did this on purpose, right? It's bad because the check disks for this information disk and this one are disjoint. And I've ordered them that way on purpose because I wanted to show you what not to do, right? If I really wanted to keep my consecutive write penalty, how many check disks I have to do, I would order these edges in such a way that if they were consecutive, they overlapped a lot. And so here is that. So here, now I'm writing these 3 information disks. Look, I only have to change 3 of the check disks. So this is better. And Charlie and Myra, motivated by this example, Myra Cohen and Dalibor Fonchek on one of the papers, defined configuration orderings of designs. Now this is a very simple design, K5. And you could have an ordering like this where you want consecutive blocks, in this case edges, to be disjoint. Or you could have an ordering like this where you have consecutive blocks. In this case, they form a triangle. Here, this can't form a triangle with these 2 without being equal to that one, right? In a graph, that's always true. So they alternate between triangles and then this thing, which is actually just a 3-path. And so that's another kind of ordering. I want to order the blocks, in this case edges, such that any consecutive 3 of them are, well, what? A partial matching, a triangle, or from a set of 3. Now, if we want to correct more than 2 erasures, we can use a Steiner triple system. In this case, an STS9, so I have 9 check disks and 12 information disks. And this has an update penalty of 3 and an erasure correction ability of 3. So, and here, what's our consecutive write penalty? Well, again, I chose this one to be bad. So 3 consecutive disks here are, oh, they're the blocks of a resolution class. So if I do a write of 3 to 3 information disks, I have to change all 9 check disks. And that's what they called a pessimal ordering. It's a configuration ordering where the configuration is, well, it's not only 3 disjoint disks in a row, because when I move to the next resolution class, it has to intersect the other two. But it's generally speaking configurations that are as disjoint as possible. They hit more of the check disk, so they call it decimal. And they also define an optimal. And an optimal ordering here, I've got 3 blocks of size 3, and I'm going to show you a picture of configurations in a second. And, well, the union of these 3 blocks is actually as small as possible in the design. So what do I have? I have 1, 2, 3, 4, 5, 6. So 3 blocks of size 3 are on 6 points. That's pretty good, right? That's a triangle as well. It has a name in configuration orderings, which you'll see in a second. And every 3 consecutive blocks in this ordering of the triples of this affine plane form that configuration, and that's the best you could possibly do. So, configurations. So here's those bad ones. Here's the good one, and this is the name from the configuration literature. Here's one if it was every consecutive pair, as if I wanted it to be as good as possible, they'd have to intersect as much as they can. It's an STS though, so they can't intersect in more than 1 point. And these are the configurations that essentially show up in the erasure correcting codes. But Charlie and Meyer and Dalibor defined configuration orderings for any configuration that you might want. Okay. Now, they pointed out that if you want an A2 ordering, that's this, that's nothing more than saying that the block intersection graph of the STS is Hamiltonian, which is a question that was asked by Ron Graham a long time ago. And Alex and Peter Horak solved that in 1988. Alex is, of course, here. And then it was solved for PVDs, for other block sizes, for different lambdas, for different intersection sizes, in a series of very nice papers by David Pike and his students, by Kathy and Boyan and Brian for PVDs. Spurred a nice set of research. Myra and Charlie were able to prove that if the order of your STS is at least 9L minus 6, then there always exists the worst possible case for your erasure correcting code. And if V is bigger than 81 times L, then every single STS admits such an ordering. So these are the pessimal ones, bad. When it comes to looking at the ones that are good, as little points in your union as possible, they were able to show that there always is an STS of any possible order larger than 15, such that it's not possible to use that as your optimal code. So it's kind of a negative result, but it's very interesting. It's an infinite construction of STSs with a nice property. And Masa Jimbo, who was here, and 2 other authors, for the 2 erasure correcting, were able to show that complete bipartite graphs have edge orderings that are optimal, and in the literature those are called cluttered. But I don't want to get into the nomenclature and exactly what that definition is. But for 2 erasure correcting and complete bipartite graphs, which are actually used in storage array systems as a structure for the disk array, that an optimal ordering was possible. Okay. Now I want to just quickly move on to non-adaptive group testing. Many people have spoken about this, but does anyone know this trick? Oh, 5? Okay, so this is this really great parlor trick. You give someone 6 cards, you ask them to think of a number up to 63, and they hand you the cards that their number's on, and you tell them what it is. And that's just group testing. So essentially you have some set of tests, and some elements, and you run this test, and if one of these is bad, the test says, oh, something's bad here. And you can zoom in on the bad elements. So there's something called the consecutive positive property, and that's when if this element is bad and this element is bad, then all the elements in between are bad. And it sounds unrealistic, but in fact it's very realistic for DNA clone matching. And I'll tell anyone about it more if they want to hear about it. And Charlie gave an optimal way to solve this problem, which I'm going to have to do super quick. Instead of ordering your tests here, like the binary representation of the numbers from 0 up to 16, you order them as a gray code, and then you put these tests in there to determine modulo 3 which elements you have. And then he had this very nice way of bootstrapping it to find any number, arbitrarily large number of positives in your pool. And again, don't have time to say, and I apologize for that. And he did it in 2D minus 1 plus log n plus 3 tests. And Muller and Jimbo and Momihara and Jimbo were able to improve that and get rid of the plus 3. And so they got optimal. They can limit the pool size, which is a common thing you want in group testing. They can correct for false positive and false negatives. And they do this by finding D2 orderings of STSs and SQSs and the corresponding packings. So again, it's a configuration order that you need. And in fact, in this one, you want the configuration order that's bad for disk arrays, which is kind of nice. OK. So as I said, there are many results out there, larger block size, PVDs, different configurations, sets of configurations. But I also want to tell people about open problems, because Charlie is always telling people open problems and spurring research. So here are some open problems if you want to work on them. Find a B5 ordering. That's that optimal thing for disk arrays. Is there an STS admitting a 3-path ordering for every admissible V? We don't know. Look into configuration orderings for larger block size. Some things have been done, but not much. Or for T designs instead of 2 designs. There's lots of work out there that, if you're interested, are good open problems to look at. OK, there are my references. There's the paper from Google. And there's a smattering of papers that fit on the page. There's more, and I can tell you more, and you can go look. And I just want to thank you all. And I want to thank Charlie for his open problems that he's given to me and to other people and pass them on. Thank you very much.
Do you have any questions, Brett? Yes.
Not a question, a remark. The disks that you described at the beginning are really servers, and there is in the last 6-7 years a lot of research on this Erasure code. They are called distributed storage codes, and there are many results there. There are results from block design. For example, there are functional repetition code, and for example, there are results there, new results about some kind of load balancing of the triple system, and I think Charlie can tell better on these results.
OK, and this just confirms what I said at the dinner. You know, you come to Charlie with a block design problem and says, oh, I know a use for that. Thank you.
Any other questions? All right. Oh, please.
Okay, I'm just curious. Is there any algorithmic results about the ordering? It's like, let's say if I have this block right here, then how efficient can I go to the next block?
Well, there are some paradigms where you can set objective functions and then algorithms for prioritizing the ordering according to your objective function. They're called F-prioritized orderings. They're also due to Charlie. I didn't have time to talk about them, but I can show you the paper that they come from.
Oh, really? I mean, this ordering that you have, right? If I give you a certain block, do you submit the next one?
Oh, like, OK, so you want to encode what the ordering is in a natural way. Sometimes there are very nice ways to do that, where you can quickly compute, but not always. That's an important problem. And it's related to ranking, unranking of gray codes and things like that. So sometimes yes, often no.
Okay. Thank you.
Thank you.
Very much.